In this video, I'm going to redo a normal distribution where you know the standard deviation of the population. I included one in the notes from the last video, but I did not do it on camera. So I want to do one for you. And then I believe your book also asks you to use the p-value method, so I'll do one like that. And then we'll get into the chi-square distribution for one variance sample testing only. Okay, so a researcher believes that the average number of hours a person spends in traffic each year is more than the national average of 46. So right now we have our null hypothesis is that the average number of hours is 46, but so far we think that it's more than 46. Assume the population standard deviation. Okay, because of this right here, I can use a normal distribution. So I'm going to have a z-score and a z-critical value. But we're saying the population standard deviation is 3.6 hours. So this is sigma. The random sample of 30 people is selected, and the mean time, so that's the population mean, is 47.8 hours. Test the claim at an alpha equals 0.05 significance level. Okay. So we think that it's one thing, but we're saying that is actually more than. So this is a right-tailed test that we're going to run. So I'm going to make my decision rule here. We have a greater than test. So we want to see what this z alpha is. And this needs to be 95%. Now, if you have memorized this, you know that this is 1.645. If you haven't memorized this, you're just going to use your little table for the standard normal and find the 95%. Oops, that's the negative side. Hang on. Here is the z table. We know 95% is in between 1.64 and 1.65. So we're going to call it 1.645, or 1.65 is fine. So if our test statistic is larger than 1.645, we're going to reject. If it's smaller, we do not reject. Okay, so we have z equals our observed values minus our expected values divided by the population standard deviation and the square root of the sample size. So same formula, just the symbols that we use are different, but we're still finding the difference between our mean and the mean that they have and dividing it by the standard error, the standard deviation. 47.8 minus 46 divided by 3.6 divided by the square root of 30 will give us our test statistic. And this number is 2.74. So 2.74 is way above it's way in our rejection region right here. So this is our z value. So we can reject the null hypothesis. There's not enough information to claim that the true mean is equal to 46 hours. 4.6? 46 hours. Okay, now let's look at how to do the same thing with a p-value. A p-value is the area underneath the curve of that statistic. So I could have found this area from my z. Here, let me draw it in with a better color. I could have found this area and said, oh, my area is smaller than the area that the critical value makes, or that the alpha is. And because of that, we can reject our H naught. So you can use a p-value to skip finding the critical value on the table. Just use your test statistic with the significance level and come up with an answer that direction. So we're going to give it a try here. A researcher claims that the average wind speed in a certain city is 8 miles per hour. The sample of 32 days has an average of wind speed of 8.2 miles per hour. The standard deviation of the population is 0.6. Okay, so that's good information. We're using a normal distribution here. At an alpha level of 0.05, is there enough evidence to reject the claim? This time, use the p-value method. Okay, so we have that our null hypothesis is that the average is equal to 8, and our alternative hypothesis is that the average is a certain miles per hour. It doesn't say, but we must have assumed that it wasn't 8 if we were running a test. So we don't know if we think it's bigger or less, so we'll just say that it's different. Okay, so we're going to go straight from this to running my test statistic. So I'm going to take my 8.2 minus 8, divide it by 0.6, which is going to be divided by the square root of 32. So this information is going to give me 1.89. Okay. Now from here, we need to use our table, but you have to be careful. Let me go find my table. Okay, so I'm going to go to 1.89 on my table. I'm going to write this number down. Oh, goodness. 1.89, 0.9706. Now, keep in mind that that area is the area to the left of your statistic. So I can draw you a quick sketch here. Oh, it's beautiful. So we have found our test statistic is bigger than 0, right? It's 1.89. So it's about here-ish. We know from the table that the area to the left, this side, is 0.9706. So this is going to take a little thought. That's not what we are looking for, right? We are looking for this area on the other side. So what we're going to do is do 1 minus that number, 0.9706, to give us 0.0294. Okay. Now that's just the right-hand side. That's not even the left-hand side. So if I wanted the total area, I need it to be two-sided, two-tailed. So I would do 2 times 0.0294. And that is going to be our p-value. So the p-value is the area underneath the curve from our actual test statistic. And this number is 0.0588. Now, that is larger than our alpha that we're testing. So the alpha that we're testing is actually the area of 0.05 split into each side. And I'm doing it very dramatic. It's not actually that large of a distance. I just want to show you here. This is 0.025. Okay, so what we found is that we're using more. Our p-value is greater than alpha. So we can tell that we do not reject the null hypothesis. Because it is using the alpha area plus more, then it's inside the do not reject region. It has more people in it than we anticipated. Which means we do not need to reject our null hypothesis. The other side of it is like over here, so you can see how much more we are actually pretty close, to their mean. So in this case, our p-value Let me write that for you. The p-value is greater than alpha, so do not reject the null hypothesis. So to answer the question, there's not enough evidence to reject the original claim that the certain wind speed on a certain city is 8 miles per hour. The only difference in this is instead of finding the number that would cut off here, our critical value for our test statistics, we found the area of our, of our actual test. You could do it either way. A couple of things about p-value before I move on to chi-squared. If your p-value is less than or equal to 0.01, reject H naught. The difference is then highly significant. It's very, very, very small area. If your p-value is in between 0.01 but less than the alpha, there's still a significance. It's just not highly significant. But if your p-value is greater than 10, do not reject H naught. Greater than 0.10, do not reject H naught. And that's just in general. The difference is not significant. Okay. I have chi-squared printed, I think. Yes. Okay, chi-squared of a single test. Now, I left this one out. It's just a little bit different than the other ones, but it follows the same pattern. We're still going to find our hypothesis. We're going to make a decision rule and find our critical value. Then we're going to find our test statistic and then make a decision. So the steps are the same. The standard deviation of exam scores in the math department of a local college is 8.6. A professor believes that this value to be less. He samples 20 exam scores and finds that the standard deviation is 6.9 at a 0.05 significant level. Does this sample provide enough evidence to suggest that the true standard deviation is less than 8.6? Whew. What do we actually need to know? Well, we need to know that the standard deviation is 8.6. Sample is 20 people. The sample standard deviation is 6.9, and we have a significance level of 0.05. Okay. Null hypothesis is that there is an 8.6 standard deviation. The alternative hypothesis, the claim that we're testing, is we think, what do we think? Professor, local college believes the value to be less. Okay, we finally get to do a left-tailed test. So we have sigma is less than 8.6. Okay. Degrees of freedom is 19 if my sample size is 20. We're going to need that information. So we're going to jump to our chi-squared table. If I can find it. Okay, chi-squared, we want our alpha. Remember this time we're looking for area on the right for chi-squared. So it's the opposite of the normal distribution. So when I'm looking for this information, if I want the right side to be 0.95, then the left side is 0.05. And my degrees of freedom, I don't remember, are 19. Ooh. So I have a number of 30.144, but that's not right. Oh, because I did it backwards. I'm looking for 0.95 area. Remember, because I'm looking for the leftover to be 0.05, and it's going to give me this area on the right. So I'm looking for 0.95 at 19 degrees of freedom. There we go. 10.117. Okay. So I have 10.117 as my chi-squared alpha, which is my critical value. I know anything that lands in this region over here is going to be the do not reject region. If I get my test statistic in this 0.05 area, which is a very small proportion of this sample, or should be a very small proportion, then I'm going to go ahead and reject the hypothesis that it is less than. Reject the null hypothesis. And say that most of my stuff must be over here, otherwise I wouldn't have got my answer over here. So I'm going to run my test statistic, my chi-squared, and the formula is right here at the top. It's the same formula that we used when we were setting up the confidence interval. So we have 19 times 6.9 squared divided by 8.6 squared to give us 12.23. Now 12.23, I had it marked, is in the do not reject region. So we are not going to reject the null hypothesis. There's not enough information to say the variance of the population is less than 86. Okay. 8.6, not 86, 8.6. In a simple random sample of 28 cars, the standard deviation of the sample in the gap between the door and the door jamb is S equals 0.7. Test if the standard deviation is greater than the population is 0.6 millimeters at an alpha equals 0.05 significance level. Assume normality with no outliers. Okay, I've gone ahead and drawn in our skewed curve here. We are looking for our null hypothesis to be that. Now they said that's really weird, but the standard deviation of the population is 0.6. So that is our null, and then our alternative hypothesis. We think that it is greater than that, so we'll do sigma is greater than 0.6. Okay, so because we're doing a greater than, then we have the right tail test at 0.05. So when I find that critical value, the chi-squared alpha, on the chart, I don't need to do anything fancy. I can just find the number, because it's already set up to find the right side area. So when I am looking for 0.05, here we go. What's my degrees of freedom? There were 28 cars, so my degrees of freedom need to be 27. Goodness. That's a large number. 40.113, 27 degrees of freedom at 0.05. So 40.113. Okay, now I'm going to test my sample. Gives me 27 times 0.7 squared divided by 0.6 squared. And that's approximately 36.75. Uh-oh, 36.75 is a large number. However, it's not larger than my chi-squared alpha. It's maybe be here, right? 36.75. Okay, so for this reason, because it's in the non-shaded area, we do not reject H naught. We don't have enough information to say that the population variance is greater than 6. I have one last problem. In a random sample of 18 machine parts, the standard deviation in lengths is S equals 12. Test if the standard deviation is less than the 13 millimeters at alpha equals 0.05. There's not enough information in this problem. I'm assuming that the 13 is the standard deviation of the population. One second. Okay, so I'm going to set it up like that's what they mean. So my null hypothesis is that sigma is equal to 13. But my alternative hypothesis is that the standard deviation is actually less than 13. Okay, so in my distribution, that's beautiful, we're going to use this tail over here, the left tail. We're going to look for chi-squared alpha. Again, goodness, be careful. We're looking for 95 on the chart, 0.95, to give us what this critical value is. Gotta stop losing my chart. There we go. What's my degrees of freedom? I have 18 in the sample, so my degrees of freedom is 17. Notice that I can't keep using the same one, even though the area is the same, or the opposite in this case. Does not mean I can use the same value, so don't make that mistake. 0.95 is the right side area, and we're looking for 17 degrees of freedom. Is that right? 8.672 looks good. Okay, so let's run it. Chi-squared equals 17 times 12 squared. So there's that number, divided by the original number squared. So if you're trying to figure out where I'm getting all this information, that gives us a 14.49 test statistic. What does that mean? Well, on a number line, 14.49 is to the right of 8.67. It's bigger than 8.67. Do not reject. And we have not yet been able to reject a chi-squared. Okay. So when you're doing a variance test, remember that you're using the chi-squared table of information, and that the right-hand side on the table is the shaded region. Good luck.